Testing network transports in isolation shouldn't require you to rewrite your entire test suite just to swap HTTP for WebSockets. We'll demonstrate how FastMCP's run server and process utility lets you spin up a real HTTP server in a subprocess, test the transport layer with actual network calls, and automatically clean up resources, all while keeping your test code clean and deterministic. You'll see the exact pattern for verifying transport behavior without polluting your main process.
Import PyTest. From FastMCP utilities tests, import run server and process. From FastMCP, import FastMCP client. From FastMCP client transports, import streamable HTTP transport. Def run server host, SDR port int, none. Function to run in subprocess. Server equals FastMCP, test server. At server tool. Def greet name, SDR. Return f hello, name. Server, run, host equals host, port equals port. At PyTest, fixture. Async def HTTP server. A fixture that runs server in subprocess. With run server in process, run server transport equals HTTP as URL. Yield f URL/MCP. Async def test HTTP transport HTTP server, SDR. Test actual HTTP transport behavior. Async with client. Transport equals streamable HTTP transport, HTTP server. As client. Result equals await client ping. Assert result is true.
This demonstrates the subprocess testing pattern for network transports, a specialized approach that validates real-world communication while maintaining test isolation. The pattern uses separate processes to simulate actual network conditions, testing the complete transport stack from serialization to protocol handling. Unlike in-memory testing, this verifies the full integration path, including process boundaries and network layers. The technique works by launching the server in a child process with a dedicated transport, then connecting a client to it through the actual network interface. Fixtures manage the server lifecycle automatically, handling port allocation and cleanup while providing the connection URL to tests. This creates a controlled environment that mimics production conditions without requiring external infrastructure. This approach matters because it catches transport-specific issues that in-memory tests miss, like serialization edge cases or protocol mismatches. You'd use this pattern when testing low-level transport behavior or validating complete system integration. The trade-off is increased test complexity and runtime cost, so it's reserved for critical path validation rather than routine unit testing. Let's break it down.
Import PyTest. From FastMCP utilities tests, import run server and process.
This imports PyTest for test infrastructure and run server and process, a utility that handles server lifecycle in tests. It isolates the test server in a subprocess, preventing state leakage between test runs.
Def run server host, SDR port int, none. Function to run in subprocess. Server equals FastMCP, test server.
This defines the server initialization function designed to run in a subprocess. It instantiates a FastMCP server named test server, which will host our AI callable tools. The subprocess isolation prevents test pollution between runs.
At server tool. Def greet name, SDR. Return f hello, name.
This at server tool decorator exposes the greet function as an AI callable tool. FastMCP automatically generates an open API-compatible schema from the type hints and docstring, enabling AI models to discover and invoke this function with proper argument validation. The pattern mirrors how you define any FastMCP tool, decorate the function, specify typed parameters, and return a serializable result.
Server, run, host equals host, port equals port.
This starts the FastMCP server on the specified host and port. It blocks execution until shutdown, handling all incoming tool calls and maintaining the connection pool. Without this, the server would never actually listen for requests.
At Pitest, Fixture, a sync-def HTTP server. A fixture that runs server in subprocess. With run server in process, run server transport equals HTTP as URL. Yield F URL/MCP.
This is Pitest's fixture pattern for reusable test setup. It spawns a FastMCP server in a subprocess for each test, then yields the server URL with the /MCP endpoint path. The context manager ensures the subprocess terminates after the test completes, preventing resource leaks.
A sync-def test HTTP transport HTTP server, SDR. Test actual HTTP transport behavior. Async with client. Transport equals streamable HTTP transport, HTTP server. As client. Result equals await client ping. Assert result is true.
This test verifies HTTP transport functionality by connecting to the server fixture. The context manager handles connection lifecycle, ensuring proper cleanup after the test. It validates the most basic operation, ping, before testing more complex interactions. Subprocess testing pattern. The run server in process utility provides complete isolation for testing network transports, automatically handling server lifecycle, port allocation, and cleanup. This approach is slower than in process testing and should only be used when true subprocess isolation is required. The fixture pattern shown here keeps your tests clean while maintaining strict isolation boundaries.
The server that disappears during testing becomes the most reliable server of all.